Okay, catalysis. So rates of chemical reactions can be affected by the conditions, right? We can change the rate by changing the concentration of the reactants. We can change the rate by changing the temperature, right? Both of those methods for adjusting the rate have limits, okay? If you have a reaction that's occurring in aqueous solution and you want it to go faster, you can't heat it above the boiling point of the solution, right? Because then it's not going to be the same reaction anymore. It's all going to be in the gas state, and it's going to be different. Some things that you might want to speed up, if you heated them up too much, they would decompose, right? Reactions occurring in your body, we can't have this reaction occurring at a high temperature and this at a low temperature because they all have to be at the same temperature, your body temperature, right? So a catalyst is the other way to change the rate of the reaction. And what a catalyst does is it increases the rate of the reaction without being consumed. So it's not just that we're adding more of one of the reactants. The catalyst does not get used up. And how it works is it provides an alternate mechanism in which the rate determining step has a lower activation energy. So let's look at our energy diagram here. So this is the decomposition of ozone. And so this is one elementary step, the uncatalyzed reaction. We've got O3 plus O. It goes through a transition state, and then you end up with two O2 molecules. The activation energy is relatively high, so the rate is going to be slow. So ozone just by itself does not decompose rapidly. It'll just hang out there. The problem with the ozone layer is when we get chlorine atoms in the atmosphere. Those catalyze this reaction and make it go faster. So the chlorine provides another mechanism which has lower activation energy. So this would be the catalyzed reaction. This one happens to have two transition states, but they each have activation energies that are much lower than the uncatalyzed reaction. The rate constant is equal to the frequency factor times E raised to the negative EA over RT, the Arrhenius equation. If you make the activation energy smaller, then the rate constant gets larger, the reaction's faster. So here's a mechanism for the catalytic destruction of ozone with chlorine as the catalyst. So if this is a good mechanism, then these reactions must add up to the overall reaction, right? So we've got a chlorine on each side. That's the catalyst. What tells me that this is a catalyst and not an intermediate is that it appears as a reactant in the first step. It gets destroyed or used, and then it gets regenerated. That's the opposite of what happens with the intermediate. The intermediate showed up as a product in one of the early reactions and then got used up and doesn't show up in the overall reaction. So this is a catalyst. It's here as a reactant and as a product, and so it's not going to appear in the overall reaction. And then I have O3, and that doesn't cancel out anywhere. And then I have ClO and ClO. This is the intermediate. This appears and then disappears. So that also drops out. Catalysts and intermediates both drop out of the final reaction. So O3 plus O gives 2O2. That make sense? So here, the rate-limiting step has a much lower activation energy, so the overall reaction occurs at a faster rate. The chlorine is not consumed in the overall reaction. So where do the chlorine atoms come from? Well, they come from chlorofluorocarbons, CFCs, like things used in refrigeration. They used to be used in aerosol cans. And the CFCs themselves aren't the problem, but they get into the atmosphere, and light from the sun causes them to dissociate and produces those free chlorine atoms. I'm not going to test you on these specific applications of catalysts, but I think it's helpful to see how this relates to real life, not just sitting in the science lab. So a catalytic converter. Here in California, all the cars that have been made after a certain date, I have a really old one that doesn't have one, but the catalytic converter is on your car's exhaust system to get rid of some of the pollutants. So a catalytic converter has solid catalysts in it, things like platinum, rhodium, or palladium, and they are on a high surface area substrate. So they're on a substrate, something else, that has a high surface area, because you wouldn't want to have just a solid block of platinum. It's very expensive. And that's why sometimes people steal catalytic converters, because they have valuable metals in them. It's like people stealing copper wires out of houses. I'm like, man, really? I think you could earn more money if you just went out and got a job. Anyway. Yeah, I suppose. Okay, we'll get away from sociology or whatever that would be. Okay, so exhaust pollutants such as nitrogen monoxide and carbon monoxide then are converted into less harmful substances, nitrogen and carbon dioxide. Nitrogen and carbon dioxide are normal parts of air. Now, we don't want too much carbon dioxide in the air, but it's still not a harmful substance in and of itself. So this also promotes complete combustion of fuel fragments. So when your gasoline burns, it doesn't necessarily all burn into CO2 and H2O. And so you can end up with fragments left, and I can't use, I have this really love-hate relationship with this stupid pointer. Anyway, that's a fuel fragment. Now I'm not pointing in this. In the catalytic converter, this reaction, this combustion, can be catalyzed so that it goes all the way to CO2 and H2O. Thus, we're not getting fuel fragments into the atmosphere. So here we have just a schematic of how that would work. It's got a ceramic substrate, and then the catalytic metal is put on top of that. You want a large surface area because you've got exhaust gases coming through here. And so the larger the surface area, the more likely they will encounter the catalyst and the reaction will occur. And then hopefully you've got much less harmful gases coming out of your exhaust. Any questions? So there's different mechanisms or different types of catalysis. Homogeneous catalysis is where the catalyst exists in the same phase as the reactants. So here we have homogeneous catalysis. The catalyst is in the gas phase and the reactants are in the gas phase. They're in the same phase. And so an example of that is the catalytic destruction of ozone by chlorine atoms. It's all occurring in the gas phase up in the air, in the atmosphere. We also have heterogeneous catalysts, hetero meaning different. Here we have the catalyst in a different phase than the reactants. So in our catalytic converter, the catalyst was a solid, and the reactants, again, are gases passing through the catalytic converter. So that's called heterogeneous catalysis. This is interesting. I'm not going to test you on this. So what's really interesting, there's usually much more below the surface when you start studying something. And so, we're concerned about the depletion of the ozone layer, and we know that chlorine catalyzes that. Is that the end of the story? No. There's this thing called this ozone hole that develops over Antarctica over the course of the summer. So here we have images of the ozone layer over Antarctica in May and in September. And in September, there's this big hole in the ozone layer. And if you just looked at the 1 year and you came to September and you're like, oh my goodness, all of the ozone is going to be gone. It's just going to keep going, and oh no, right? But then, strangely, what happens is, over the course of the year, you come back around the next May, it looks like this again. And then this happens again. And so it comes and it goes. It's called Antarctic spring. So what happens is the chlorine atoms are evenly distributed throughout the atmosphere. It's a really big volume. So why are we getting this depletion in this one area? So the chlorine gets bound up in substances such as ClO and O2. So it combines with other things, and that, when it's bound up like that, then it can't catalyze ozone destruction. You're like, well, good. Let's get more of that stuff up there, right? In the polar stratosphere, the clouds have ice particles. Those ice particles catalyze the reactions that release chlorine from their bondage. So on these ice particles, these reactions occur, and chlorine gas is released. And then in the Antarctic spring, the sunlight dissociates those chlorine molecules, breaks them down into two atoms. And now we have chlorine atoms that can catalyze the reaction, the decomposition of the ozone. So that's going to keep going until those clouds melt away. When the clouds melt away, then the catalysis of this reaction goes away. These chlorine atoms get bound up again, and the destruction of the ozone slows way down. And so it's going to regenerate. The result is we get this ozone hole that forms every spring, lasts around 6 to 8 weeks, and then it goes away again. So there's two types of catalysis occurring here. Any questions about that? So, if you're interested in the environment, chemistry is a really good thing to study.
I have a question.
Yeah.
Do you know why it is that it happens only during a certain time of year?
Yeah, so the reason it happens only during a certain time of the year is that those clouds are only present at a certain time of the year. And they are what catalyze the release of the chlorine atoms. And as it gets warmer over the summer, then they melt. And then the solid ice particles aren't there anymore. Yeah. Any other questions? So here's another reaction. The reaction between ethene. Remember, this ene suffix here means that it has a double bond. These are hydrocarbons. You'll learn a lot about these in OChem. This is ethene. It's got 2 carbons. It's got a double bond here. This can react with hydrogen to form ethane. That's a relatively slow reaction at normal temperatures. But if you have finely divided platinum, palladium, or nickel present, it will catalyze that reaction and cause it to occur rapidly. The large activation energy of the reaction is due to the strength of this hydrogen-hydrogen bond. In order for this reaction to proceed, that hydrogen-hydrogen bond has to break. It's a strong bond and it doesn't want to break. But the catalyst weakens that bond because the hydrogen adsorbs onto the surface of the platinum or other metal, and that puts strain on the hydrogen-hydrogen bond. Have a picture of that? Yeah. So here we have our hydrogen and our ethene. And these metals will adsorb these gases. So the gases will just kind of stick onto the surface of the metal. So the hydrogen sticks on here, and the ethene sticks on here. And then they actually diffuse on the surface so that they can move around a little bit on the surface. So we have adsorption, we have diffusion. So the hydrogen molecule actually separates into atoms. Then we have the actual reaction where the reactants are forming the ethane, and then you have desorption. So this is another example of heterogeneous catalysis. You've got these gases, they adsorb onto the solid. This is, rather mysterious process, right? How do they move around? Do they have legs? What's going on there? We're not going to worry about those details. They react here, and then once they react, they desorb, they go back off. Any questions? Okay, biological catalysts, enzymes. This is very, very interesting. And this is going into the area of biochemistry. So most of the reactions needed for an organism to survive are too slow under normal conditions. It's not going to work out. So your body is one example of this. Your body uses enzymes to catalyze the reactions that are needed. These enzymes are generally large protein molecules, different than what we were seeing of metal atoms and chlorine atoms. Here we have these large protein molecules that catalyze reactions. The way this works is we have the reactant molecule is called the substrate, and that will adsorb or bind to a particular site on the enzyme. It's called the active site. And it binds there through intermolecular forces. So dipole-dipole forces, induced dipole forces, or hydrogen bonding. And when it binds through those intermolecular forces, it generally puts strain on some of the important bonds, and that lowers the activation energy for the reaction to occur, and so it occurs faster. So in very, very general terms, here we have the enzyme plus the substrate, and the substrate will bond to the active site. That's fast. Then the enzyme substrate complex will break into the enzyme again and the product, and this is the slow rate limiting step. So here we have our substrate, our molecule coming in, and it'll bind on this active site. So we get this complex, and then the reaction occurs and the products are released. Any questions? Let's look at a specific example, the digestion of sugar. So, table sugar is sucrose. Sucrose is a disaccharide. So it's actually two different sugars bonded together. So there's a glucose part and a fructose part, and they're bonded here on this carbon-oxygen bond. So we need to break that one bond so we can get sucrose and fructose, and then those are going to go and do other reactions. So the overall reaction here is we've got sucrose plus water forming glucose and fructose. This is called hydrolysis because we're adding water to the molecules. So our enzyme is called sucrase, and enzymes are often named relative to the thing that they catalyze, relative to the substrate. So this catalyzes the reaction of sucrose, and so it's called sucrase. So a lot of enzymes will have ASE as their suffix. So the sucrose bonds to this. The enzyme has oxygens and hydrogens here that will hydrogen bond with the sucrose molecule. And it's shaped such that when these bond, which is very favorable, it puts strain on this bond. It like pulls it tight, and it's like really easy to cut it. So it's much easier to break this bond when it is strained, and it's strained because the enzyme is holding the molecule in a specific position. Any questions about that? So enzymes are amazing. They give the organism tremendous control over which reactions occur and when they occur. And so your body can control the reaction that's occurring by either producing or destroying the enzyme, or sometimes activating or deactivating the enzyme. So each enzyme is very, very specific. It catalyzes a single reaction. So it only works on one sort of thing. And the factor by which it speeds up reaction is really big. It can be as much as 1 billion times faster. So a reaction that really just would not go at all to one that's going very quickly. There are substances that can inhibit enzymes, and they'll do that by blocking that active site, and then the enzyme can't work anymore. Substances that inhibit enzymes can be very, very toxic. It's a lot of what insecticides are. They will inhibit an essential enzyme in the insect, and then the insect dies because an important reaction can't happen. You lock up a single enzyme molecule that can prevent the reaction of billions of substrate molecules. So it's not like you have to go in and destroy all the substrates. You just have to destroy this gate, this enzyme.